the seminar for today, it's my deep honor to introduce David Ginley from the National Renewable Energy Lab in Golden, Colorado, where he is a fellow and chief scientist. He has a really broad interest in materials, as I think most well represented in the fact that he is a former president of the Materials Research Society. And his sort of application scope is mostly in the area of solar energy conversion and solar energy storage. And today he's going to talk to us more about the latter part of that, where he's going to tell us about computational identification of materials for solar energy conversion and using, in particular, solar hydrogen as an example. Let's welcome Dave Ginley.
So thank you, and I appreciate all of you coming, and I appreciate the invitation very much. Hopefully this will be stimulating, and I certainly welcome questions, whatnot. I'm going to talk about particularly the idea of how do we predict complex things like water splitting. And I have to give a lot of credit here to my cohort. This is Vlad Stevanovic. He was originally at NREL, and now he's a professor at the Colorado School of Mines. Vlad is the theorist, so when you start asking me really detailed questions, I'm going to just surrender and say, ask Vlad. The work actually derives from sort of a dual origin. One is I've been involved in water splitting for a while. You'll see how long in a bit. It's almost embarrassing. And then we had one of the original EFRCs. We have the Center for Inverse Design. This has been transmorgified into the Center for Next Generation Materials by Design, incorporating metastability, which is our current EFRC. And I wanted to give you a brief sort of synopsis of what it's doing and how this all connects. So most of you know about the convex hull. I didn't, actually, originally, until I was educated. It's a theorist construct. Experimentalists don't normally think that way. But if you look at the thermodynamic equilibrium potential for a series of different materials, you find that there's one material that sort of sits at the bottom of the convex hull, and that's the equilibrium thermodynamic material in a system. So given that kinetics and things like that didn't matter, you'd always end up there. But of course, that's not true. And in reality, we have all kinds of metastability. And so one of the things we want to do in the center is begin to look at metastability. And in particular, there's three kinds of metastability that we're interested in. One is polymorphs. So what's a polymorph? It's like TiO2, where you have anatase and rutile. And lots of materials tend to have all kinds of polymorphs. And so how do you calculate those? How do you say what their thermodynamic stability is? And then how do we understand which one we're likely to have? Alloy systems, where we have variable stoichiometry across a range. And then finally, the system that maybe we're the most interested in for a lot of the electronic applications, which is defects. And if you want to consider doping a defect, then doping. And the goal is, first of all, to be able to understand how to calculate all these for normal materials. And then the goal is to understand how to transform them from one state to another. And so the transformation phase introduces the idea of kinetics. Just like if we're going to do water splitting, eventually we have to face up to the fact that we have to deal with kinetics. And so the whole goal of the FRC is to begin to understand how to first principles calculate kinetics. And I won't give you an answer because we don't have one. But why do we care? So most of you are aware, and it's come up at least 3 or 4 times today, that if we continue to penetrate the market with solar, eventually we're going to have energy storage. And if we have to have energy storage, how are we going to do it? Well, some proponents go batteries. No problem, we'll just use lithium batteries. That could be problematic just because of the cycle life. Others go zinc air, which actually might work. You can go fuel cells, but in the end, you need some energy storage media that has a pretty high density that's transportable. And so one of the ideals, and this is from the days of Bacchus long, long ago, is the hydrogen economy. And people have been advocating the hydrogen economy, and then they've been de-advocating the hydrogen economy for many years. And part of the problem was that hydrogen isn't necessarily the easiest to get, and it's certainly not the easiest to store. Although we had a conversation this morning, Andrew and I mostly, where there's 2 new vehicles being launched that are actually hydrogen fuel cell cars. And both of them use high-pressure hydrogen and don't seem to have any qualms about that at all. So maybe if you can store it as high-pressure hydrogen, then the question is, how do you generate it? So I love this because it shows that maybe we're not as original as we thought. So Jules Verne said, I believe that water will one day be employed as fuel, that hydrogen and oxygen, which constitute it used singly or together, will furnish an inexhaustible source of heat and light, the intensity of which coal is not capable. I believe that when deposits of coal are exhausted, we shall heat and warm ourselves with water. Water is the coal of the future. 1870. So great vision. Jules Verne actually was quite a visionary. We're still not there yet. Fortunately, we haven't run out of coal. But at the same time, it says, let's see, our current alternative fuel plan, ethanol, takes much more energy to produce than it yields. Whereas our new alternative fuel plan, hydrogen, will also take as much energy to produce as it yields. This plan doesn't make any sense. Maybe not, but you don't realize how much energy went into producing it. And then I could produce an alternative fuel plan if you want. So maybe we need to think how we would use it. And so I think that if we look, the hydrogen economy is possible if we can come up with hydrogen in an easily usable large amount. It's heavily used in industry. Nuclear heat, we'll let that go. Electrolysis, can we get it out of nuclear electric? We can certainly generate it out of a wide range of solar thermal, biomass, natural gas. We can even get it out of coal. And we can use it in a bunch of different ways. And so I think that as we look at potential uses, hydrogen has an immense enough market already and increasing that it's got enough depth, shall we say, that it's worth thinking about how we want to generate it economically in any case. You can think about a sustainable energy economy based on hydrogen, certainly. And maybe that will come to pass. Again, it's been a long-term vision that if we can get water and decompose it into hydrogen and oxygen, and this is Honda and Fukushima, who many, many years ago, in the early 75 kind of time frame, first demonstrated that you could split water with strontium titanate, then maybe we can enable fuel cell cars. And of course, what we'd like to do is we'd like to do it with the efficiency of silicon. And that's the real problem, is how do you get that very high efficiency? So what does it take? It takes materials, interfaces, catalysis. Can theory coupled to experiment help? If you'd asked most people that a few years ago, they would have gone, absolutely not. Sorry. However, I think the answer now is the inverse. I think we've gone through a really dramatic transformation in science where now computational material science actually can drive experiment. And this really is a new way of doing business. So we're going to talk about how we can apply it to PEC, and then we're going to talk about, okay, once we have that model, how do we identify new PEC materials, and then maybe we can combine 1 and 2 to actually generate the success. So you kind of have 3 options if you want to look at it that way. You can do photosynthesis, which, well, it's really not very efficient. And it's not going to get a whole lot more efficient. So that's probably not going to be a good solution. You can do photovoltaics with high-pressure electrolysis, and that probably is a potentially usable route. The photovoltaics are now getting quite efficient, but you have to have a high-pressure electrolyzer that's equally efficient, and that's still got some basic material science. And then finally, maybe you can do the best of both worlds. You can combine a semiconductor and a liquid junction to do the conversion directly in aqueous media. And whether you believe in it or not, it's a really interesting science challenge because it combines sort of semiconductor photoconversion with electrochemistry in a way that is very useful for us to understand. So the energetics are what really are the problem. So you have a counter electrode, you have your semiconductor, you actually have some kind of band bending, you have a band gap. And the problem is that although the water couple is only about 1.23 volts to get oxygen and hydrogen, in reality there are overpotentials on both sides that drive the needed potential to around 1.6 and 1.7 ideally, and most practicable systems have been in the order of 2 volts, which is starting to get to the point where you're a little bit over where you'd like to be in terms of the band gap of the material. So this is what sort of it looks like, and obviously where your semiconductor band edges are important. Where this couple sits versus them is important, and how to get there from a first principles calculation is not entirely trivial. I thought I would just tell you that, you know, in reality, there are other ways to get there. I stole these from John Turner, and they're just as complex as they look. The idea is that you could use a tandem configuration, and here they use gallium arsenide and gallium indium phosphide to generate a bigger voltage. And of course, in a tandem cell, you capture more of the solar spectrum theoretically, but both of these have to have fairly large gaps. The reality is that you can get conversion efficiencies on the order of 10 to 12%, but it's an immensely complicated system, and you haven't really solved the stability at the interface problem. And so you still need to do that. So this shows you, what does this show you? So this is the idea that you can put a catalyst on the surface, and I think this is actually meaningful. This is actually high temperature growth of the material and then water splitting using a ruthenium-based catalyst. And I think that, you know, what it says is that catalysis can make a big difference. We don't know what the right catalysts are right now, nor do we have a good model for how to do this. The very first use of ruthenium oxide on the surface was Adam Heller at Bell Labs, again, a very long time ago, and I don't think we've substantially improved on this. The Caltech hub originally proposed a structure like this. They're now doing something different. This is very hard to realize, and it's very hard to realize in a practicable way. So you have to go back and think about it. This shows you a high-pressure electrolyzer and sort of what the curve looks like. So at least if you look at hydrogen generation rate versus the electrolyzer efficiency, at low rates you can get pretty substantial conversion rates on the order of 80%. As you go up in current, though, to where you really want to be, that falls off pretty dramatically. Yeah?
That seems counterintuitive to me because kinetics say otherwise. You know, once you hit sort of an activation energy, you should start at low current, at lower currents, the overpotential is higher, but for higher currents,
Well, so they use a catalyst. So at low currents, there's lots of catalyst available. As you begin to push the current density, you start to run out of the ability of the catalyst to keep up with the reaction. So your overpotential actually starts to go back up. Because your loading is so high. I mean, you're talking about really staggering current densities.
Right, but your catalyst loading is so low.
Yeah, your catalyst loading is pretty low.
Okay, thank you.
Because otherwise, if you put too much catalyst in, then the cell is too expensive.
Right.
So Absolutely. So that's another one of the holy grails, right? If you can, and that's in general true in fuel cells, in electrolyzers, this whole, can you get cheap catalysts that do what expensive catalysts do while having a very low overpotential? That's the holy grail. There's definitely more than one Nobel Prize there if you can figure that out. So please do. The rest of us would be grateful. It's non-trivial, I will tell you. So if you look at conversion efficiency, and I thought I would just put this in so you kind of have a marker. If you look at the Shockley-Queisser efficiency, so first of all, it's just, if you absorbed every photon, what would your efficiency be for a particular band gap? There are lots of normalized metrics, but if you do that, and you look at silicon, for example, it says that silicon at 1 sun ought to be 29%. And there's a couple of companies now that are at 25.6. So that's pretty impressive. It also shows that you can get most of that Shockley-Queisser efficiency ultimately. And so when you talk about PEC, you have to keep in mind that if you combine that electrolyzer we showed you with this silicon solar cell, that's what you're competing against, really. Okay, so we talked about this. What are we really interested in? We're interested in understanding how we can calculate where the band edges are so that we can decide whether we have a proper position to actually do water splitting. And what we'd like to be able to do is we'd like to have a good solar absorber, about 1.5 volts, that's catalytic enough. It has to straddle those potentials. It has to have enough overpotential, and it has to be stable. So there's a lot of things that, in terms of first principles calculations, we're not very good at in that. And the question is, can we begin to address it? You know, are there models? So I told you I would show you that I'm really old, so I am. And back in the dawn of time, Mike Butler and I published a paper, 78, on looking at the absolute flat band potential versus the conduction band minimum for a whole series of oxides. And we found, quite surprisingly, that when you correct all the energies to the point of zero charge, which is that point at which there's no absorbed differential between hydroxides and protons, that you get a wonderfully straight line for virtually all the oxides. And so why do I bring this up? Well, because this is the kind of correlation that we're obviously looking for, but we'd like to be able to derive it from first principles calculations instead of, in our case, it was empirical measurements that took me a couple of years to do. So how do we go about this? So what we'd like to do is we'd like to understand the factors that are important. So the flat band potential is clearly one of them. The conduction band maximum is another. Then there's the difference in the Fermi level between the conduction band and the Fermi level, which is delta FC. There's a pH-dependent term, which I said is this point of zero charge. And then there's a dipole factor, which is due to the interaction of the water molecules on the surface, which is essentially the Helmholtz layer. Now, so if we take this curve and we try to figure out, we can basically throw this out. It's a very small term. We can throw out the pH term if we're at the point of zero charge. And then we have to look at the dipole. And we find something very interesting in the old data, which actually I will show you seems to be true even in the new data. And we don't understand it, but it's actually quite useful, which is that at the point of zero charge, the dipole contribution is essentially 0.5 volts for everything, even non-oxides. So I don't know quite why that is. I would expect that the water dipole would have a slightly different structure, but it appears to have almost identical structure for a whole range of materials, and I'll show you that in just a second. So then, if we can calculate the values for the CBM in water, which we can equate from a CBM value in vacuum, plus this 0.05, then we have the CBM value in water, at least conceptually. So all we have to do is calculate this. Well, that turns out you have to figure out how to do that because our standard methodology doesn't give you a calculated band position versus anything. It does it in absence of everything. So what we're going to talk about is how do we calculate the ionization potentials and the electron affinities. So we do this in 3 steps. So first, we use DFT plus GW to do a calculation. So if you just do DFT, you're probably aware you don't get very good band gaps normally. So, but if you do DFT plus GW, you get a correction for the valence band minimum and conduction band maximum, and those tend to be much more accurate. So this gives us a calculation of the bulk value, but not given versus any reference, right? So then we do a calculation where we use DFT and we break it into slabs and we do an electrostatic calculation, and we can then connect the slab to the vacuum level. If you can do that, then you can find where your electron affinity and your ionization potential are as a function of where your valence band and your conduction band positions are. And that seems to work pretty well, as I will show you. So the ionization potential is simply going to be the change in voltage between the valence band from DFT bulk and the valence band from the GW calculation. I see excitement or something.
This is exactly how we do it. Yeah.
Perfect. So then it's correct.
Well, it's something that we doesn't matter. We can talk about it.
Okay. So there's some more details here about how we actually do it. So GW starts from the same underlying DFT using GGA plus U. We'll talk a little bit more about that later. The charge density has to remain basically constant, and there's got to be self-consistency. And we look at local field effects. There is a little bit of a special treatment for 3D transition elements. You have to put in the external D potentials, and Vlad can explain that much better than I. But the bottom line is if you do this and you take that same kind of plot that we showed before and you look at it, we can now plot basically a straight line for oxides and non-oxides together. And so it looks like it really does work in predicting where you'd expect the band gap and the minimal band gap to be. So then we have to look at surface effects. And what we did is we assumed that we would use low index surfaces initially and or non-polar surfaces, because these are typically what you find in these materials. And we know non-polar surfaces don't reconstruct a lot, and they're also low energy. And so from the literature, this is some of the orientations. And then what we can do is we can plot these all as a function of surface orientation, the experimentally measured, so this is versus photoemission data. It's too bad Antoine isn't here because he could tell me where some of the missing data is. So the photoemission data is the bars, and the calculated numbers are the solid lines. And the first thing you notice is that it's actually pretty good. The agreement is actually pretty remarkable. You notice that in some cases, like tin oxide, different surface orientations have vastly different photoemission energies. And so this tells you that if you're right about which one's the important one, that's fine, but if you're not, then you're going to be off substantially. And so we blow this up a little bit, and you can see just how big this is. That's almost 1.5 volt change between the low energy surface and some of the other surface energies. And what this says is that if we're ever going to do this really well, we're going to have to be able to go back and calculate all the surface energies that you might get in a polycrystalline assemblage. And so we're actually doing that. I'll show you that for one particular system in just a couple minutes. But I think that the take-home message here is that the agreements here are actually pretty good between the calculated data and the actually measured photoemission data. So, okay, not bad. There is definitely an orientation dependent. There's been a number of measurements that look at this, and they see the same kind of trends across a wide variety of samples. So what we did is we calculated essentially all of the orientations of tin sulfide. So tin sulfide is a new PV material that people are excited about. There's a lot of people, especially Roy Gordon and Antonio Bonacisi at Harvard and MIT, that are beating on this. It's not a particularly efficient system now, but it seemed like a good system to calculate because it has, the surface orientation is very important for that system because we don't know how to make even good ohmic contact to it right now because of all the different surface energies. And so what you can see here, and this is a very recent paper which you can't even see where it came out, is that there's a pretty big variation in surface energy across tin sulfide as a function of its orientation. And I think this is illustrative of what we see for pretty much any material. And what it tells you is that we really have to start understanding, and we don't yet, computationally, why when we make a polycrystalline material, we get a set of particular orientations. We don't get an average of all of these. We get particular orientations depending on how we grow the material. And so how to derive that so we know what these energies are is one of the challenges that we don't have the answer to right yet. But this does show you how important it is. So can we relate what we showed you in the photoemission data to electrochemistry? So the answer is, actually it works pretty well. So this shows you the hydrogen and oxygen potentials mapped against where these energy levels are. And these are the band edges. And this is the experimental data. And no, the theory data versus the experimental data. And so we know which systems split water, and so far we have a pretty good concurrence on which systems ought to split water and which do. We're pretty good on where the potentials are, but there's some mismatches that we have yet to solve. So some systems are pretty far off. This is, again, the tin oxide, where we have to be very careful which orientation we have. You can see the same thing occurs in TiO2, which of course is one of everybody's favorite water splitters, is that depending on the orientation, there's a lot of different surface energies you can have. Fortunately, most of them will split water. And then strontium titanate is right on the edge, but actually splits water, one of the best materials. But it shows that we're close. We're getting there. So what about this 0.5 EV? Where does that come from? Well, we don't know fully, but what it tells us is that the basic Helmholtz layer, the dipole layer, is basically identical for all these materials, or very close to it. Are there actually other measurements of that? So the answer is yes. So it turns out that some of the references to the point of zero charge for some of these materials are still mine, so you can throw those out pretty much. And there hasn't been this, so the point of zero charge is very important technologically because it drives how you make latex paint, for example. You know, how do you suspend the nanoparticles of TiO2 in the paint so they don't agglomerate? It has a lot to do with the point of zero charge. So DuPont is very interested in it. Dow's very interested in it. But they don't publish tables of the point of zero charge for different materials. And so one of the challenges here is we have to go measure a whole lot more of these to make sure we're accurate, because if we're not accurate, then our 0.5 volts might not actually be right. And you can see that there's a pretty good variance in what the reported PZC is for these materials. And so it's important that we get better measurements. However, if you look at like H2O absorption on layered chalcogenides, I love this. The difference is like from 0.2 to 0.7, oh, the average is 0.5. And in general, they see just about exactly what we're reporting. If you look at, I had to put it in, perovskites, you see the same thing. You see about a 0.4 EV shift. So it appears to be pretty ubiquitous. So maybe we're just that insensitive. So if we can get the PZC right, now what would be really great, hint, hint, is to be able to calculate the point of zero charge for a material, which has a lot to do with those different surface orientations and how essentially acidic or basic they are. So if we can do that, that would be great. So if we correct those, then we get a pretty good correlation indeed for a set of normal PZC materials. So the bottom line is that we have a pretty good model now for being able to look at the VBM and the CBM for a range of materials that are of interest for water splitting. We can get from first principles where those edges are and where they are versus the water couple, and we can get an idea whether this should be a water splitting material or not. Whether it's stable or not, we still have to do some work, but at least we're a lot further along in being able to model the system. So then the question becomes, so what? If all you're doing is modeling stuff that we already know, then it isn't that important. So there's another part of computational material science that's been evolving, which I think, as an experimentalist, is totally cool, which is, how do you predict missing materials? And how do you go beyond what our normal lookup table of ICSD is? And so we can, right? And so the idea is that, why do we care? So if we look, for example, at the A2BX4 chalcogenides, we only have seen 255 of the materials that could exist in the ICSD, and there's 429 that don't occur there at all. Now, you could first just say, oh, those are all just unstable materials. So that's the problem. But in reality, it turns out that's not the case. And so as we calculate these, what we do is we first have to look at what structures are. And so we look across a range of essentially 40 or 50 structures that can occur. And then we have to look at stability with respect to competing phases. And then we have to look against the elements in the standard state and the other competing binaries and ternaries. And if the thing is still stable, then it probably ought to exist. We ought to be able to make it. You still have to get into price and synthesis space. So, for example, so we want to sample prototype structures. So what we do is we do DFT plus U to sort out ground state structures out of 39 possible structure types. So, for example, I'll illustrate this with the spinels. We calculate those 39 structures, we calculate for every one of the possible spinels. And we look for what the ground state is. So this is not a small calculation. Fortunately, NREL has Peregrine, which is a petaflop machine. You have to do essentially 80,000 GGA plus U calculations. When we first started Peregrine up, we used 100% of its time, and we were told that was unacceptable. I don't know why. Something about other funding. And then we've developed this Pilota algorithm which helps detect errors and makes the calculation much quicker. So once we do that, then we have to look at elemental reference energies, which means we have to calculate versus the chemical potential of the constituent elements. This turns out to be both hard and not so hard. So it's hard because if you use DFT directly, you're kind of hosed. You can see that this is per atom. So if you look at EV per atom and then and you just use DFT or GGA, basically, it's hopeless. The information you get isn't going to give you any decent thermodynamic information. So we talked about this today. We put in this FERE constant, which, as far as I'm concerned, is a fudge constant. But it turns out it's a constant fudge constant, so theorists say it's okay. It's about, sorry, but that's what they tell me. So it includes about 0.054 EV per atom as a correction factor. And once you put that correction factor in, then all of a sudden, you're well below 0.1 EV per atom, and all of a sudden those numbers make a lot more sense. But this is for binaries. So the question is, what happens when you go to ternaries? And
Sorry, what is the FERE? What is that?
so it's a correction factor based on the elemental reference energy. And as far as I can tell, it's a constant for all transition elements. And you'd have to get Stefan or Vlad to explain it in better detail. But what it allows them to do is, even on ternary materials, it allows them now to calculate the heat of formation reasonably accurately because there's not this big dispersion from DFT anymore. And as far as I can tell, from what we can tell, it actually is correct. So whatever it is usable, right? So what we've done now is a lot of calculations on materials in the database and not materials in the database. We use VASP and PyLATA to help the speed. We use the NREL Peregrine, and we get a very large database of enthalpies. It allows you to look at the compound stability with respect to decomposition against other phases and against the binaries and the elements. So what does this look like really? So this is where the connection from theory goes to experiment. And this, from my viewpoint, is transformative. So this is calculated, right? So as you calculate other phases, so these are competing phases, you knock out a chunk of synthesis space. And ultimately, when you look at the chemical potential for synthesizing, in this case, it's the manganese 2 silicon 04 spinel, what theory tells you is you ought to only be able to make it in this range. This is the only place where it ought to be thermodynamically stable. And so, again, you can look at all the competing phases. This tells you that in this range for the chemical potential of oxygen, you ought to be able to get this phase. It's a pretty narrow synthesis range, actually. Interestingly enough, when you look at the literature, the only place they get this is right in that range. So now we have a connection between theory and synthesis, telling us where we can make something. Now, that doesn't tell you anything about the kinetics, which is hopefully something we'll get to, but at least tells you that in this range, it ought to be thermodynamically stable. So going back, it says, okay, so now we ought to be able to apply this to other systems, and we ought to be able to look at where things are stable. So it works great for a broad range of the spinel materials. In fact, we always, if we can make it, we always end up in the range where they say we can make it. We haven't found anything outside that. So how do we apply this? So we now have, I'm going to go through these really quickly, but I think it's just amazing, because I didn't realize this when we started. So if you look at all the possible spinels, and this is oxides, you have the A atom, the B atom. Things with check marks are things that have been made. Things with the open squares here are things we don't even expect to be able to be made. And things with question marks are things that actually ought to be thermodynamically stable but have never been made. So the first point is there's a lot of them. You know, this is far more than what we expected. Now, one thing is there's obviously probably a non-trivial synthesis pathway into these. And we were asked, you know, I remember when we started the EFRC originally, like 6 years ago, Steve Chu came by and said, well, so what have you predicted that and made that wasn't predicted before, that people didn't know? And the answer at that time was no, none. But that's not the answer anymore. So if you look more, you can see that there are ones that we expect to be stable that haven't been made. There's ones that we don't think are going to be stable, and there's ones that we really don't know. Probably most of the ones that we don't know means that you're not going to be able to get to them. If you look at sulfides, the number of the pluses is actually much larger. And if you look at the selenides, again, there's a large range of materials. Now, this is interesting because a lot of these materials are potentially solar cell absorbers. They're active optoelectronic materials. They're all interesting. Also, we went back and looked at the ABX materials, and you can see that of those, there's also a large number that are predicted to be stable but have never been made. There's a large number of the 1, 2, 5 family, in fact, much larger number that should be makeable that haven't been made. And also for the 1, 3, 4 family. So the key thing here is that if you're just using ICSD as your guideline, you're missing a very significant fraction of the possible materials. Now, maybe not all of these can be made, but at least theory says that all of them are accessible if you can find the right synthesis approach. And some of them have very interesting properties indeed. So again, you can see there's just a tremendous number. So what happens? So here we looked at the 18 electron ABX materials, and this is a very complicated, I realize you probably can't read it, which is actually maybe to my advantage. That a check mark is reported, a plus is stable but not reported. A circle is unreported, undetermined. A dash is unreported, probably not stable. A red circle is successfully synthesized, and a blue circle is something that we believe we have a synthesis route for. So the key thing here is there's a non-trivial number of red circles now. So these are materials that were previously unreported, that theory told us should be stable, that we went and made and are stable. And so this is, to my knowledge, and although Garrett Cedar says there's one battery material that falls in this category too, this is the first real example of changing our paradigm about how we search for materials. Instead of sort of eclectically hoping to find a material or using our intuition, we now can actually look at a broad space, identify potential candidates, and some of those are actually makeable. Now, what's interesting is some of them have very interesting properties as well. But as I said, it's very non-trivial to be able to get these from the synthesis, because it tells you it's thermodynamically stable. It does not tell you what the synthesis route into it is. So, you know, we successfully synthesized the rubidium copper telluride. These all failed because they have incongruent melting. These failed because they all reacted with the container. And these failed because we don't know. But as we get a better understanding of the synthesis, we hopefully can go back and put that in, and then we'll know which ones we might be able to get to by which route. Now, it's pretty ambitious, obviously. So out of 100 A2BX4s, there's 100 new out of 429 unreported. Out of the ABX, we predict that there ought to be 235. This is a pretty large fraction of the materials. And many are earth abundant, and some have very interesting properties. So for example, we made the tantalum cobalt tin. And you would have looked at that and gone, oh, a metal alloy. Who cares? It's boring. Well, it turns out that tantalum cobalt tin has a band gap of about 1.7 eV. And actually looks like it might be a very interesting solar absorber, even though it's all metal. And so there's a lot of interesting materials, properties. So we've only talked about stability, right? So the next step of this is to take those materials that are now predicted to be stable and crank them through our functional computation to try to figure out whether they have interesting functionality. So we can search for water splitting, we can search for solar absorption. There's a lot of different things we can look at once we know how to do this. So I'm curious, you know, what are sort of the length scales that we can do this over? And, you know, as we move on, we're interested in how do you apply this sort of methodology to materials, processes, and structures? And why do we care? Well, this is why we care. So in essence, we're down here. We're predicting new materials. We're beginning to predict order. We want to begin to scale into process and technology. But at the other end, they've already started up here. So if you look at the Dreamliner was computationally designed and built and was only wind tunnel tested after it was constructed. The first time that's ever been done, that they used the computation, they had enough faith in the computational model to make the airplane. Fortunately, it worked out okay, except for the battery part, but we already told you about lithium batteries. So the real question is, can we eventually connect all these together? Can we begin to connect the materials discovery with process technology to get to real technology? And I think you're seeing that evolve. I think we're in the middle of a really dramatic paradigm shift in theory and experiment. And I think that's really exciting. So in conclusion, I think that theory is beginning to be able to describe this interface and beginning to address photoelectrochemistry in a way that is at least potentially predictive. I think we're beginning, or maybe we're more than beginning, to be able to identify new materials where we can actually predict structure, composition, and whether they'd be stable or not. If we can combine all this, we certainly can search for new PEC materials, but we can search for all kinds of materials of new functionality. And then I think the next step is we have to integrate more of the surface chemistry, and we have to understand kinetics to begin to understand the chemical reactions. If we can do that, we'll be able to fully describe the PEC device from first principles, which would really be exciting. Thank you.
The questions from the audience? Yes, back here.
I'm interested in this mysterious 0.5 electrovolts. So I'm wondering that you show that this number is quite stable with different types of surfaces, even including oxides, selenites, and so on and so forth. But I'm wondering if you have difference in surface dipoles, for example, polar surfaces and non-polar surfaces, and those surface dipoles could introduce differences in water structures around that surface. Would that actually change this number by how much?
So there's two effects, right? And we have to be a little careful that we don't confuse them. So one is how, well, I say acidic and basic the surface is, but that's really more a measure of whether it likes to attract hydroxyls or protons. And so that plays a huge role in defining where your band edges are. And so a lot of times, if you change the surface chemistry, you change the surface's ability to attract protons and hydroxyls, and you can shift band edges by a couple tenths of a volt really easily. So that's a big effect, and we can only compare measurements at a point at which the surface charge from the protons and the hydroxyls is zero, right? And that's the point of zero charge. The other is the smaller effect, which is the ordering of the water dipoles at the surface. And I would have guessed that the length scale of that ordering would depend more strongly on whether the surface is polar, nonpolar, et cetera. And all the evidence to date says that it's not a very strong function of that, which means that maybe just water is that ordered no matter what, and you're just sticking it as an ordered interface on top of the electrode. But you know, we see that roughly the same amount almost no matter what the material is. And they have a very big difference in how polar the surface is. So I don't know the answer. That's something we need to understand better.
Just following up on that, I don't know why you call it one number. It's 0.5 plus or minus 0.3, right? So basically, that error bar is like 60% of the magnitude of the shift. So if you have like one of the materials is probably 0.2, the other one probably is going to be 0.8. So there is probably a physical difference between those two. Doesn't that limit the predictive ability of using this 0.5 value?
So I guess it depends on where the error comes from. If the error comes from the actual dipole, then yes, I agree. It says there's more functionality there than we think. If the error comes from the fact that we measure the PZC so poorly that the error's there, right now that's clearly the error. That we're not measuring the point of zero charge well enough for these materials to really compare that. So I'm not sure 0.3 and 0.5 and 0.7 are different. It may turn out that they are, and then that may come back to your comment that there's some ordering difference depending on the polarity of the surface. And I don't know the answer to that. I mean, I've asked the same question and we just don't have a good enough answer. The only way we're really going to answer this is to go in the lab and measure enough point of zero charges to become comfortable with that, you know, that we have good data there, and then look at where the flat band potentials are.
So given the complexity of photo electrochemical catalysts and just the tough part in the coupling the system, and I asked this of everyone who does PEC, why not just use this kind of search to do electrochemical catalysts, get the electrons in no matter how you can, and don't worry about how the photons or how the electricity gets there? Because it seems to me that if you focus on the electrochemical catalyst issue, and you can generate your electrons, you know, hydroelectric, wind, PV, geothermal, whichever, then you've got a nice systematic decoupling and an easier problem because the surface doesn't have to be photoactive.
So I can answer that two ways. One, we're really interested in direct conversion, and this, of course, is equally relevant to PV, where you have to understand the surface energies to make ohmic contacts and things like that. So there's really use to being able to understand whether you can predict where your band positions are. In terms of the catalyst, by definition, a catalyst is a kinetic entity. We do not know how to first principles predict kinetics very well. Maybe you'll argue, but at least I have no clue. And we're beginning to look at that, right? So we're trying to do that, but we really don't have the full tool set to be able to do that right now. So we can't search across kinetic space. Eventually, I think we're going to be able to look at a nanoparticle or an ordered inorganic cluster and look at what would happen if you did electron transfer to oxygen or to, you know, a water molecule. But right now, we really don't have all the tools to be able to do that.
Just to comment on that, I mean, there are tools, but they're very expensive. You couldn't do a mass, you know,
Right.
genome search, basically. That's the problem, is that to do it right is very expensive and time consuming.
So what we'd like to do is be able to correlate functionality with something we can do high throughput calculations on. And that, we don't have that yet.
I suspect I suspect that this 0.5 volt shift that, you know, you use as sort of a, you know, a correction is due simply to the fact that you have a polarizable medium. You have this water layer, okay,
Yeah.
that is leading. I don't think it's ordered. It's not ordered. It's a liquid. So I mean, there may be some instantaneous ordering, you know, near the surface, but of course it's fluctuating because it's a liquid. But it's giving you some idea of an average polarizable effect, right? That is essentially changing where you think the band edges are. Which is an important point that, you know, to understand.
Actually, that's a good point. If that were true, then if we went to acetonitrile or something,
you should see something different.
you should see a constant maybe, but a different constant because of the polarizability. We can do that.
Yeah.
We can do that experiment. That's a good idea, actually.
I'll just have one last question. You mentioned that these materials, a lot of them have yet to be synthesized. What are the synthetic route options for these? Is this from the melt? Is this from vapor deposition? Is this CVD? What are the routes toward making these materials?
That's a really good question. And so what we found is that for the ABX materials, PVD approaches seem to work okay. For the spinels, they crashed horribly. Why, I'm not sure, but solution-based synthesis approaches worked. And especially hydrothermal growth worked well. There's something about the materials that we haven't easily discovered that says something about the synthesis route being more difficult or trickier than our normal put it in a pot, heat it up, let it cool down, right? And so I think that there needs to be some thought about, given where these might sit and how deep their potential well is, et cetera, on how to get into those and what synthesis techniques might be the best to do that. We certainly don't have a good correlation right now.
You have to calculate the phase diagram around the stoichiometric point, otherwise you don't know what to do in making single crystals at least.
That's right. Sure.
You don't need the whole phase diagram, but plus minus 10% in composition, you need that phase diagram.
Yes.
Yeah.
And actually, we're pretty close to being able to do that. That's actually not so hard.
Yeah, that's thermodynamics. It's much easier than kinetics.
Exactly.
The synthesis is, you know, there's a million routes, right? There's an infinite number of potential routes using chemistry. I mean,
That's right. But of that million, maybe 900,000 fail, and right.
So
You have to figure out which ones are more likely to succeed.
it's going to be dictated by kinetics.
Well, and the other part of this is, in all honesty, these are all thermodynamically, they should be thermodynamic equilibrium compounds, right? But you ought to be able to get a lot of them as metastable materials, because if some way into them is thermodynamically stable, there ought to be other ways that give you the metastable version. And we certainly know that for a lot of our common materials, especially in thin film form, they're metastable. So that, I'm curious at how far we can push that as well.
If there are no more questions, join me in thanking Dave Ginley.